Hey, Jiaming, thanks for joining us. I've been very excited for this conversation for a while. So what is Dream Machine?
So Dream Machine is a foundational video generative model. At the release, we were having two features that are critical to it, which is text to video, where you can type in the text prompt to generate a video, or image to video. And you can have an image plus text to generate a video.
Why don't we start with the story of 3D capture, right? Because that's really the first research and product milestone that led to the development ultimately of Dream Machine.
Luma was mostly doing things like 3D reconstruction, 3D capturing. So in this video, we are showing you can take a drone and you fly the drone around some landmark to capture a video, and then the Luma application will transform that video into a 3D scene that you can interact with. And of course, you can also do that on your cell phones to capture objects that are closer to you. But essentially, making things representable in 3D and being able to interact them was the initial kind of a product that we have. Then we were thinking about how we can not only do reconstruction, but also do generation. So we then released this app called Genie, which allows you to generate 3D assets from text prompts. And it was definitely the first one of this product in kind that we got there. And I think we started releasing the preview at around early November last year. But then as we moved along into working more and more on 3D with a lot of the best people in 3D in our company, we realized more and more that 3D data has this scalability issue. And if you compare that with images, everyone can use their cell phone to take a photo or take a video. Whereas if you try to do the same with 3D, it's very difficult. You either have to have professional knowledge about how to use these tools, or you have to use multi-view capture techniques that are still not as nearly accessible to everyday users.
Right.
So there is a vast gap between image, video data, and 3D data.
How did you solve that problem?
Yes. One thing that we realized is that in the last year, there has been many works that tries to solve 3D from quite a different angle. Instead of trying to use only 3D data, they try to use 3D as a application of a 2D foundation model, such as an image model. So in this case, you first train a diffusion foundation model, and you leverage that vast amounts of data. And then you try to fine-tune this model on multi-view images. So just like the problem that we mentioned earlier about the model not being able to reason about different size of an object, it actually turns out that being able to do fine-tuning on top of it leverages benefits from the both worlds. So it not only gets this semantic knowledge about what an object in the world should look like, it also leverages the 3D data to know about how these objects look in multiple size. So a very common solution nowadays is to use multi-view 2D generative models that are fine-tuned from the flat non-multi-view versions of that, and then try to convert these representations into a 3D object. And here I'm showing two kind of representative works on this direction.
Okay, so once it became clear that using 3D, reasoning about 3D as a fine-tune of a 2D foundation model was a feasible path, what came next?
So for us, it's quite natural. So, the limitations of images was that it wasn't able to reason about how the camera works in the world, because it only has a relatively independent shots of different objects. The next thing that is quite natural for us is to see if we can learn and capture 3D knowledge from by learning from videos, because videos naturally have a lot of these innate observations. For example, there's camera movements, there's object movements, and we are hoping that having a video model can leverage these things and try to learn something 3D about the world. Yeah. And it turns out from these type of videos, we are able to show that a video model is able to reason about 3D quite well, which in some sense is unexpected before in the community.
What was most surprising about this?
People will talk about different things about what surprises them. But I think what's really surprising to me is how large scale of compute is mostly all you need to capture a lot of the like intricate effects that people spend years to develop in like graphics and physics simulation community. And I will show some like more examples in details in just a second.
Great, yeah. So just so I'm playing this back correctly, you're saying what we're looking at here is a few samples of Luma Dream Machine generations.
Yes.
Right? That were able to reconstruct a 3D scene.
Yes. For example, in this case, what we do is we literally took one of the videos from the last slide and we put this video into our 3D reconstruction pipeline. And it turns out that it is able to reconstruct a 3D scene at this direction quite reasonably well. So the pipeline was quite simple. We take some image and then we convert that image to a video, and then we put the video into 3D reconstruction. And it turns out that it was pretty 3D consistent.
Yeah, so this is pretty mind-blowing.
Yeah.
I think we should take a second to just talk about this.
Yes.
You just said the pipeline started with an arbitrary image.
Yes.
That image then became the prompt for the Dream Machine video model, which then outputted a video that you were able to pass through into a reconstruction pipeline and get a structurally consistent 3D scene outside the other end.
Yes.
What does that tell you about what Dream Machine is doing?
So I think that tells me that Dream Machine is definitely able to reason about 3D better than any of the models that we've worked with before. And this is very much unlike like even the models that you try to obtain by fine-tuning on the raw fine-tuning on 3D data, because there is just a lot more videos and it was able to capture things in like much greater detail than the resolution that was possible for multi-view image models.
Right.
And also the simplicity about this pipeline is also very attracting. And that, like 3D reconstruction without having to take very complex captures has always been a thing that we are trying to solve. We've considered multiple approaches to solve this problem because we acknowledge the fact that despite how NeRF and Gaussian splats were super popular in the research literature, when you try to deploy these techniques in the wild, there are many issues that comes with this imperfect capturing system that comes along. Like people, when they're trying to capture an object, will oftentimes not capture the object fully 360 degrees. There might be motion blur associated with the camera. The object might be moving, so it's better to have them like perfectly still. So all of these are limitations that we were trying to solve like before we even started trying to develop the Dream Machine.
I see.
So this is very exciting to us as well because it also shows that there is, a very interesting alternative path towards solving like 3D reconstruction.
So here, this was the first, I guess, attribute or first clue that you had that video models might be doing more than just generating interesting frames.
Yes.
That there might be an inherent understanding of the world.
Yes.
Right. And 3D consistency was the first clue. Mm-hmm. What were some other clues?
These are some videos that we tried on some like NeRF datasets. And naturally, because a lot of us work on NeRF, like Gaussian splatting and reconstruction. So the context here is that we put the first frame of an image into Dream Machine, and then Dream Machine will give us the output as a video. So as you can see here, like the 3D consistency of the generated video looks quite amazing. And here are some like more examples, all from very popular NeRF datasets. And if you work in the domain, you will definitely know what these datasets come from.
Could you just tell people what a NeRF is?
Okay.
So, what is a NeRF and what is a Gaussian splat?
I see, sure. So a NeRF is more like, it's a full name called the neural radiance field. And the idea is to assume that the world is simulated by volume rendering techniques. And we, based on this assumption, which is obviously imperfect, we try to solve in this 3D field, what's the color and what's the opacity of this point. And then the rendering happens by integrating a long array of line. And then oftentimes things are like just non-opaque at some certain like location. And that's how we get the rendering out. Of course, having one view is not sufficient enough to solve this problem. So in the case of NERF, there is oftentimes like a very detailed multi-view, like input, for example, images or video, such that these problems can be solved. One quite interesting breakthrough at that point was how realistic these reconstruction can be compared to the older like photogrammetry-based methods. And because these methods can reflect the lighting changes and complex physical effects are much better than the existing photogrammetry techniques. But this is also from the 2020s, so a lot more techniques have been improved since then. One example being Gaussian splatting. So you can think of it as another type of representation based on like volume rendering that is much more efficient than the existing like NERF-based techniques in terms of how like rendering works. So it made kind of an interaction with these objects possible because you can render things at much higher FPS than before.
Gotcha. So what are we looking at here?
So here we are looking at a video generated by Dream Machine where the input is an image frame. So this is a very common example that people use in like 3D reconstruction. In the case of NERF, there will be like many images like that surrounds this object, and the goal is to reconstruct the 3D object and then re-render them like back. It's a very interesting setup because you can see that the table is not fully reflective, but you can see how the lights are like reflecting on the side of the table as you change your like viewing angles. And that at that point was quite a revolutionary for NERF to do because photogrammetry techniques won't be able to kind of reason about this type of physical effects just yet. But what's really surprising about Dream Machine is that we almost did nothing with regards to these NERF datasets or have zero 3D priors into how the model works. But the model just by itself learns to kind of uncover these interesting physical aspects of the world just by generating an image to video. The second example is from this paper called the Zip NERF. And here we are also given first frame of the image and try to generate 5 seconds of video on top of it. What's the really interesting thing we can check it is the reflections of the background in the TV. So as the camera moves, the TV's like reflection also seems to move consistently with what seems to be in the physical world, which might be a window that shines light onto this TV thing like there. So that's another kind of a few interesting like physical properties that is being like appeared onto this traditionally NERF theme. Again, this is only one image compared to in the traditional NERF sense, you have to take hundreds of images with almost perfect accuracy.
So I think it's just worth calling out what's happening here. You're saying a single image was passed through the Dream Machine as a prompt.
Yes.
Dream Machine was then able to reconstruct a scene in video. And that video has consistent 3D light transport.
I think it is, yes. So yes, I'm not an expert on like graphics to fully say like how physically accurate it is, but at least I think it looks to me to be quite physically compelling. So maybe if we run this through the perfect simulator, we will see some discrepancies as of now, but still I think the results are quite compelling and quite realistic compared to any of the models that we see.
So one surprising capability that that Dream Machine was able to handle was modeling the world in 3D.
Yes.
What other capabilities were you surprised by when Dream Machine was done training?
Yes, because we work on 3D, so naturally there are many properties that are in 3D that we definitely care about, and we are very surprised to see some of these problems being like solved just implicitly in the model. So one example is the depth, which is very obvious thing that people care a lot about in like 3D modeling. There's a tons of research on the like topic of depth, but we are just going to show some videos that clearly shows that the model has an understanding about depth. So for example, in this video, it's an image to video case. So the model is able to know that the person is in the foreground, is closer to the camera than the background. A similar case happens in this video as well, where the subject is closer to the cameras, and this is reflected when you see the camera starts to turn. And similarly, in even like more abstract cases, you can see how this notion of depth appear, where the center of the like circle turns in the smaller distance than the circles that are like outside it. Similarly, there can be some quite non-trivial camera move changes that are just emerged from this type of reasoning. And not only still things, but also some cases where the subject is slightly moving. For example, this person tilts their camera up. And there's also cases where the depth is pretty clearly reflected in the case of falling leaves, where there are falling leaves that are closer to the camera, and then there are also falling leaves that are like further from the camera. Another interesting aspect of these things is also light transport, where this is also a very heavily investigated topic in graphics. So for example, in this case, what we are trying to look at is as the camera turns, the red neon sign of Luma goes from the right to the left of the video. And this is reflected on the person's left side as their jacket is slightly reflective of the red color. And you can see more and more of this like red color being seeped in. So this is clearly something that is quite difficult to simulate in traditional graphics cases. Similarly, you can also see that, like for example, in this cute animation, you can see that as the bear is wobbling inside, the water by itself is moving, but also the reflection of the bear on the water is also moving with the flow. This other video shows how it can simulate how light goes through semi-transparent materials as the camera slowly turns. You can see the leaf on the foreground has more light shine through it as the camera turns. So these are also all quite tricky. So one thing we want to compare, of course, is how does it work against regular nerf captures. So this is something that nerfs are traditionally much better at than photogrammetry. But unfortunately, this case requires hundreds of images to perform well. With Dream Machine, we just took another coffee machine that we have in the office and then just do image to video, and we can actually see a lot of the light reflections on top of the metal surface of the coffee machine being simulated by the model. And similarly, there are also some very non-trivial dynamics, such as how water moves, how furs move, that can be done in the video models. And this is also an example from like having animals, image to video of animal. It requires definitely a lot of the understanding of how furs move and the dynamics of things if we solve this problem from a more traditional graphics pipeline. And not only that, we can also simulate like very compelling or interesting like camera motions because of this innate knowledge. Similarly, we can see how as this giraffe moves, the shadows also moves like alongside it, so that the model definitely has a knowledge about how light works like when things are moving. This is another example where we show that like in the exploding room, how things are floating together as the camera moves in forward. And this is another case where we show that behind the person, there is like interesting like cloth that are moving. And if we try to simulate all of these with traditional graphics pipelines, like the cloth simulation part will by itself be quite difficult.
All right, so fair enough. We've got a video model now that, as you just showed, can handle a ton of capabilities that traditionally would have taken explicit graphics pipelines, right? Mm-hmm. No game engine required, no volumetric reconstruction required.
Yeah.
We can handle 3D structure, it can do depth, it can do light transport, it can do dynamics, right?
Yes.
But if I'm being, let's say, ultra rigorous about whether these video models really understand what's going on in reality.
Yes.
The holy grail is causality. Am I right? You kind of want to understand and see evidence that Dream Machine, if it's actually doing more than just generating cool frames, it ideally should be able to start predicting what changes in the world must happen.
Yes.
When given some input.
Yeah.
Some indication that it has an understanding of Newtonian physics or state of the world, all and be able to reason over the entire state space of things that should happen when you throw a ball or my pen falls off. Do we have any evidence that might indicate that there's something more going on in these models than just pure frame to frame prediction?
Yes, totally. In the previous types of video models that people have access, typically it's more like an image animator. So the image takes part in the majority of the scene, and then it's mostly like moving without cuts. However, as we know in like movies and such, there's a very common thing, which is things like transition to different cuts of they're taking a video of the same subject inside different angles. For example, in this case, the task is image to video. So we basically give this a close-up shot of this cute, like furry little monster, and we just ask it to do image to video. So there are two interesting facts about it. The first interesting fact is that it generates a cut, which is again not seen in like previous video models. The other thing that is also interesting about this is that the background and the subject, which is the monster, in the second shot looks basically the same as what is in the first shot. So you can see that this is a blue furry little monster, and in the second shot is that even though it's like taking a shot on the background, the monster is still blue and furry. So you get the impression that this is a video about the same monster. And also the environment is also similar, where you have this like red ground underneath and the blue kind of a forest on top of it. Even though we haven't really asked the model to do anything about it, the model is able to reason about the second shot being a cut of the first shot that happens to have the same things in the first shot. So this is definitely some kind of a non-trivial cause and effect that happens like even in a not entirely like physically possible scenario. Another example here I want to show is that, again, this is an image to video. So it might look a little bit disturbing in the first frame, but the first frame contains what we want to give to the dream machine. So in this case, we are showing a very unnaturally looking eye looking at a girl that is standing like in front of the eye. In the first shot, that is the input to the dream machine, the model, like the image does not contain the front face of the girl. There are two interesting facts about that. First, the dream machine generates the second shot, which is a close-up shot on the girl. And secondly, this girl looks very like terrified.
Right.
And this is possibly caused by this eye being very unnaturally looking. And this is some kind of a cause and effect that is like even harder to reason like strictly in the physics, but more delving into how just human psychology works. So I think the causality is definitely deeper than physics alone, and is going into other aspects that we as humans can't explain well about. Another interesting fact about this frightened girl close-up shot is that if you look at the first shot, the girl was wearing a blue dress and it has a short hair. And the second shot is basically shows the same thing.
Right.
So it's also suggesting that these two shots are basically different views of the same thing.
Right.
So I think this is also another evidence that the dream machine is able to reason about things that will happen, or like even at like different angles in a matter that is quite non-trivial to reproduce using traditional methods.
So this is pretty remarkable, right? Mm-hmm. Basically, there's a representation of reality that the Luma dream machine model is exposing that is able to maintain semantic consistency about what should happen in the world.
Yes.
With zero explicit design from you guys around that. Mm-hmm. So is causality essentially just an emergent property of choosing the right data?
I would say yes. It seems that all the evidence that we are seeing points toward that.
Got it. So this is pretty wild because Dream Machine is able to simulate the causality of reality purely through looking at camera cuts.
Yes.
Just by observing how camera angles in videos change.
Yes.
And the consistency of characters across those cuts.
Mm-hmm.
What's going on under the hood? What did you have to do to get that causality to show up?
Again, this is not much. I think the biggest factor are the scale of data and the scale of compute. And I think we also get a lot of questions about whether there are, more explicit priors being like baked into this. But the answer is no. Like there's really not much prior that is being baked into these models. And this follows roughly how the bidder lesson tells us.
Right. Cool. Okay. Any other capabilities?
Yes. So I think the other interesting thing that we showed slightly earlier, but also want to kind of re-emphasize here, is how Dream Machine is able to reason about the non-physical world as well. Even in cases where it's in entirely a scene of art, it is able to, first of all, do camera changes and also introduce like new concepts into the scene by just using the model. So again, if we were trying to reason about the world via the traditional kind of physics techniques, it is very difficult to kind of reason about things inside a totally fictional world. So I think this is something that more happens like inside our dreams rather than happening like inside a physical world. And it is like something that is very close to what humans imagine. And therefore, it's also an evidence that shows that maybe trying to be too fundamentalist about physics might not solve these problems. This is another example like from the same friend that we're showing. This is like a very abstract figure of the input image is just a line inside the circus. And the Dream Machine was able to imagine the scene of this is inside a performance. And this concern line was just like vanished under this magic trick. So again, this is a totally kind of abstract scene that would not make any like physical sense, but overall it has this artistic effect that is going on.
Where do we go from here? What comes next? And what are your conclusions from seeing all the sort of emergent properties of reality that Dream Machine can simulate?
Yes. So I think, obviously, one of the next steps to do is to improve the model on all fronts, including resolution, efficiency, prompt following, being able to control with more precision, and so on. And the team is actively, kind of working on it. But I want to take it a step further about like what we have in mind. So one of the examples here that we are showing is we mentioned earlier that you can actually get 3D from 2D. So I don't think it's much of a stretch to say maybe we can get from like videos to 4D. So that's being able to do world simulators, meaning that you might be able to simulate multiple angles at the same time. So I think towards that goal, I think it's definitely something would very much be interesting to have. Another really interesting aspect is to see how much unlock we can get by having a more intelligent multimodal agent. So, in this case, we've only demonstrated, the interaction between text and like video and image modalities, but human perceive the world in many different factors. For example, humans also hear the world and also interact with the world differently. So I think it will also be very interesting to see how we can make further unlocks by going into this multimodal AI route, where we combine all the signals that we can get and try to develop AI that learns from these signals together in a joint manner. And I think currently, we are only at a very, very basic stage at being able to like generate videos from text and images at this stage. I would say this is more like as you said, research preview or version 0 of the model. I think the more intelligent model will be able to kind of handle more complex inputs and more complex requirements that arise both from the product and requirement standpoint, and also from what it means to be intelligent. So our goal is to be able to create these multimodal AI that are that can achieve this in a efficient and compelling manner.